welcome back. This is Unit 4.1 on bonding, and we're going to start off talking about ionic bonding. All right, so we've talked about elements a lot, and so this is really the first unit where we're going to talk about how elements come together to form compounds. So let's look at the big picture of ionic bonding. So we are going to start with, say, for example, sodium. All right, so we have sodium, and we're going to talk about valence electrons as well. So if we look on our periodic table, we see that sodium is in group 1. So that means that it has one valence electron. And so we represent that with a single dot like this that's around sodium. And let's say that we are going to bond this with chlorine. Okay, and if we look at chlorine, it's in group 17. That means it has 7 valence electrons. So if we were going to represent that, we would do 1, 2, 3, 4, 5, 6, 7. So these are what's called, these pictures that I've drawn are what is called Lewis dot structures. And we place the symbol, and then we put dots around it that represent the valence electrons. So if we remember back, the most valence electrons that any element could have would be 8. So the absolute most dots that are ever going to be around an element would be 8 dots. So here we have sodium with 1 and chlorine with 8. Now, if we also remember back, I said that the magic number for the number of valence electrons is always going to be the number 8. So every element wants to have a full p shell, S and P shell, so that's going to be 8 electrons. Well, all metals, and sodium is a metal, all metals tend to want to give up their electrons because the valence shell that's right under that is going to be filled. So sodium wants to give away electrons. All nonmetals, like chlorine, want to accept electrons because they almost have their valence shell filled. So what happens is this sodium is going to give its electron away to chlorine. So chlorine is going to accept it just like that. So we have 8 valence electrons around chlorine, and then sodium, since it gave away that one, underneath has a full valence shell. So they're both happy. Now, when this happens, sodium got rid of an electric charge from the electron, and electrons are negative. So that's going to create an ion of sodium with a +1 charge because only 1 electron was removed from sodium. Now, if we look at chlorine, chlorine gained 1 electron, so it gained an electrical charge. It gained 1 negative charge because electrons are negative. So chlorine is now going to have a -1 charge. So because of these charges, positive charges attract negative charges. And sodium is going to be now very attracted to chlorine through what's called an electrostatic attraction. Electrostatic attraction. And these are going to kind of stick together like 2 sides of a magnet, north and south. So you're going to form a compound called sodium chloride. And so you would write it just like this. Okay, so that's the big picture on ionic bonding. And this is covered, types of bonds are covered in your book on page 262 through 267. So make sure you read that. We're going to talk here in this table about the 4 different types of bonding. So go ahead and pause and draw this table out, and then we'll fill it in. All right, so this first one, you see the example there, chlorine, and then that line between the 2 chlorines mean that they're bonded together. So a chlorine bonded to a chlorine. Well, this is Chlorine is a non-metal. So this is a non-metal bonded with a non-metal. Okay, so I'm going to write NM plus NM, and the NM means non-metal. So it's non-metal bonded with a non-metal. Now, how do we know that these are non-metals? Okay, and the answer to that is because of the stair step that's on the periodic table. So metals are on the left side, non-metals are on the right side. Okay, so chlorine is in group 17, so that is a non-metal. So it's two non-metals bonded together. Okay, and this is called a covalent bond. Covalent, when two non-metals are bonded together. All right, and the next one, hydrogen bonded to a non-metal. Now, this is what we call an acid. Okay, this is an acid. And the description is hydrogen plus a non-metal. Okay, so hydrogen, all acids except for, all acids begin with an H. The only two compounds that begin with an H that are not considered acids are going to be water. We're not going to call water an acid. We'll talk more about that when we get to acids and bases. And hydrogen peroxide, which is H2O2. Okay, that's also not considered an acid. So anything that begins with a letter H, like this, is considered an acid. It's an H, hydrogen plus a non-metal. Okay, and so how do you know? Well, it's hydrogen plus a non-metal. So any non-metal that's here on the right side of the periodic table. So hydrogen plus a non-metal. All right, the next type of bond, which is what we're going to be concentrating here in 4.1 for this week, is called an ionic bond. Ionic. So copper bonded with chlorine is called an ionic bond. So the description of that would be a metal plus a non-metal. Okay, so if we look again at the periodic table, the stair step, copper is going to be over here with the metals. Okay, you mark out that, put two non-metals there, just to make that clear in your notes when you go back and look at it. So in an ionic bond, we're going to have a metal plus a non-metal. So one from the left side of the stair step and one from the right side of the stair step. All right, and then our last type of bond is going to be copper as a metal, and so copper bonded with copper, and this is going to be called a metallic bond. Okay, and the description is a metal plus a metal. And so again, if we look at the stair step, we have metals here, non-metals here. So we don't have any non-metals, but we have two metals or more, two or more metals that are bonded together. All right, and so those are the four types of bonds that we're going to be talking about. All right, so let's talk about metallic solids first, and then we'll get into the ionic bonding. This is page 221 through 225. And here we have a bunch of metal elements that are hanging out together. And this circle here with the positive represents the nucleus of the metals. And then you see this hazy area around all of these nuclei. And that hazy area represents all the electrons that the metals have. Now remember, from electron configuration, metals are in the d, transition metals are in the d orbital. And that d orbital has those 10 electrons. And so these metals that are transition metals are what we call electron rich. They have lots and lots and lots of electrons just hanging out there. And so this is what gives metals their property, because all of these electrons there, we refer to that as a sea of electrons, because there's just so many electrons, a vast number of electrons. These electrons act like little tiny ball bearings for the nucleus of each one of these atoms to slip around. And then all these electrons start being shared or passing between the different nucleus of all of these metals. And so when these electrons act like little tiny ball bearings for the nucleus, it causes them to be squishy. And we know, if you remember having to deal, or our discussions in class with metals, metals are very soft. So I've talked many times about, when a pirate is given a gold coin and he wants to check to see if it's pure 24 karat gold, he'll stick it in his mouth and bite on it because that gold is super soft and it'll leave his marks of his teeth in it. And again, if you've ever gone fishing and you are putting the lead weights on your fishing line, the lead weight has these two little tabs on it that you can easily bend with your fingers to bend it around the fishing line so that it stays on the line. Okay, and because of this squishiness, metals have properties, two properties here, and they're called ductility or ductile, and malleability or malleable. And ductile means that you're able to pull it into a wire, and malleable means that you're able to hammer it into sheets. So the way I remember that is because a blacksmith, the hammer he has is called a mallet. And blacksmiths are always banging on metals after they heat them up to make it even more squishy. And so he is hitting the metal with his mallet, trying to flatten it out into sheets of armor. So malleable, flattening into sheets. Okay, and other properties of metals because of all these electrons is that they have electric and thermal conductivity, which means that electricity will pass through metals very well and also heat. So that's why the wires in our house are made out of copper, and how all of our pots and pans that we cook on are made with stainless steel or copper, because they transfer that thermal heat between them very well. So when we start mixing metals together, different kind of metals together, that's called an alloy. So an alloy is a mixture of metals. And when we do that, when we start mixing metals together, different kinds of metals, it tends to start hardening the metal up because the electrons start dispersing around more and being spread around more. So, for example, sterling silver is 92% silver and then 8% copper. That's how we get sterling silver. Cast iron, like our cast iron pots and pans, that's made out of 96% iron and 4% carbon. And stainless steel, 81% iron, 18% chromium, 1% carbon, and 1% nickel. And stainless steel, you can also mix up this percentage of chromium and maybe use other metals in that, but that's basic stainless steel. So some of the other mixtures of metals could be boron, chromium, manganese, molybdenum is MO, nickel, tungsten, and vanadium. Tungsten is W. All right, so remember these properties of metals: ductile, malleability, electric and thermal conductivity, and then remember what an alloy is. You don't have to remember these specific percentages here. Those are just some examples of alloys. All right, so ionic solids, page 213 to 218. This is where we're going to concentrate most of our time talking about ionic solids. So some examples of ionic solids would be sodium chloride, which is what we talked about at the beginning of this video. So a metal like sodium with a non-metal chlorine. And when you mix a metal and a non-metal, this is called table salt. Okay, sodium chloride is our normal everyday table salt that we eat. But ionic solids in general are called ionic salts. Okay, so that's just happens to be table salt that we know, but all ionic compounds are called ionic salts. All right, and some properties of ionic compounds are they're solid at room temperature. They have very, very high melting points because there's such a strong attraction between the two ions. And they can conduct electricity when they're in the liquid state or when they're dissolved in water. So if we do heat up these salts high enough that they actually become liquids, then it's going to conduct electricity. But the easiest way to get them to conduct electricity is just by dissolving them in water. And some of these salts are more soluble than others. So some salts do create more conductivity than others, but they will conduct electricity. So that's why it's so important that when you're using anything that plugs in, you don't have it around the shower or the bath, because if that appliance or that whatever it is that's being plugged in does happen to fall into the water, where there's all kinds of ions dissolved in the water, so it's going to conduct that electricity, and it could be fatal. You could die from it. So that's very important safety precaution. All right, so let's review Lewis dot structures and let's look at some of these. So go ahead and write these down, and then we will talk about them. All right, so lithium is and sodium both are in group 1 on the periodic table. So remember, to draw a Lewis dot structure, you're just going to put one dot around that. Now, there's a couple of rules that you want to make sure that you write down. This can only have, at most, 8 dots, okay? And it can only have, at most, 2 dots per side, okay? And then when I say side, I'm talking about north, south, east, or west sides of the symbol. All right, so lithium has 1 valence electron, sodium has 1 valence electron, so we can put that 1 dot around it. Now, it doesn't matter if you put it on the top, if you put it on the right, the left, or the bottom. It does not matter, just as long as you don't have more than 2 per side. All right, now looking at the same period 2, we have beryllium on the periodic table. And then in period 3, we have magnesium. It doesn't matter what period it's in. For the Lewis dot structure, you're looking at just the group number. So both beryllium and magnesium are in group 2. That means it has 2 valence electrons. So we add 2 dots around beryllium and 2 dots around magnesium. Now again, I could have put those dots, both of those dots, on the same side. I could have put one on top and one on bottom. It doesn't matter. Okay, now we're going to skip all the transition metals and move over to group 13, where we have boron and aluminum. And again, one's in period 2, one's in period 3. That doesn't matter. All that matters is the group that they're in. Group 13 has 3 valence electrons. So I'm going to put 3 valence electrons around boron. Now I'm going to change up aluminum. I do it a little bit different. I'm going to put 2 on this side and 1 on this side. So either way is correct. It doesn't matter. All right, and moving over to carbon and silicon, they're in group 14. That means they have 4 valence electrons. So I'm going to add 4 dots around carbon. I'm also going to add 4 dots around silicon. It doesn't matter how I put those dots, as long as I don't put more than 2 per side. Okay, so if we go back and we look at this, okay, I could not do 1, 2, 3, and 1. That would be incorrect, because I can't have more than 2 per side. Okay, now nitrogen would move over, is in group 15. That means it has 5 valence electrons, 1, 2, 3, 4, 5. Or we could do 1, 2, 3, 4, 5. Okay, and oxygen has 6. 1, 2, 3, 4, 5, 6. Silicon has 6 also. 1, 2, 3, 4, 5, 6. All right, and when we get to fluorine, fluorine has 7, chlorine has 7, so we do 1, 2, 3, 4, 5, 6, 7. And there's not much variation you can do on this, except for I can put 2 on each side, 2 at the bottom, and then 1 at the top. All right, and then finally we get to group 18, or 8 valence electrons, and there's only one way to do this, 2 on each side. Okay, so these are your noble gases that have that valence shell filled. Both the s and p orbitals are filled with a maximum number of electrons, so you have 8 dots. Now, you can only have at most 8, so never, never, never put more than 8 dots around a symbol. Now, I have seen before on test or something, let me move this down just a little bit. When I ask you to draw a Lewis dot structure, say we were going to draw it for phosphorus. So phosphorus is in group 15. It has 5 valence electrons. I have seen on a test before, somebody does it like this and puts all 5 dots on top. Or they do the total number of electrons. So phosphorus has 15. So they do 5 there, 5 there, and 5 there. Okay, so that would be wrong. So remember, it's only valence electrons. So you'd have no more than 8 ever, and only 2 per side. So don't make this common mistake here. You know, and I know you giggle about that, but it happens all the time. So don't make that mistake. All right, so let's talk about formula writing and nomenclature. Nomenclature is just a fancy word that means naming. And we're going to just talk about ionic compounds only. And we're only going to talk about main group elements for now. We will talk about transition metals, but for this week, we're just going to concentrate on the main group elements, and then we'll get into the transition metals. So go ahead and write your notes on it, but we're just going to concentrate with the main group. So again, remember, main group elements are these and these. It does not include the transition metals. All right. So the first thing that you want to make sure that you do or remember is that the net charge, so net means overall, the final charge must equal to 0. And we're working with positives and negative ions. So the positive ions are called cations. The negative ions are called anions. So that's not anion or cation. It's cat, ion, and an ion. Okay. All right. And so here we have sodium and chlorine together again. And this was our example. So this positive charge is going to cancel out this negative charge. So it's going to have a net charge of 0. So that's why we have NaCl written out this way. Okay. But what if they don't cancel each other out? Well, see, here we have magnesium. Magnesium is a +2 charge. So it has a +2 right here. And then chlorine is a -1 charge. Now, in order for this to have a net charge of 0, how many of these chlorines are we going to need to cancel out this +2? Well, if each chlorine is a -1, we're going to have 2 of those. Okay, and so that's why when you write the formula, you're just going to write Mg and then Cl with the 2 right here. This is called a subscript. Sub means under, script means to write. So you're going to write the number under the normal, like not in the same plane as these symbols. So subscript of the 2 there. That means that you have 1 ion of magnesium bonded with 2 ions of chlorine to make that compound. Okay? And so that's pretty simple when you have things like this. But what if we had aluminum that has a +3 charge bonding with oxygen that has a -2 charge? So how can we make that come out to 0? Well, there's this technique called swap and drop, and it works every single time. And the way that works is you take just, let me erase this here, you take just the number of the charge. So we're just going to take this 3, and we're just going to take this 2. So we don't use the positive and negative charges. And we're going to swap them. So the 3 is going to come over here, the 2 is going to come over here. And then we're going to drop them down to subscripts. So the 2 is going to drop down, and the 3 is going to drop down to a subscript. So aluminum is going to have a subscript of 2, and the oxygen is going to have a subscript of 3. So when we do that, it equals out to a 0 net charge. Well, let's look at that. So we have aluminum and aluminum. Each aluminum is a +3 charge. So if we were to total that up, that's going to be a +6, right? So if we have oxygen and we have 3 oxygens, each oxygen is a -2 charge. Okay. So if we total that out, that's a -6 overall. So you can see here that +6 and -6 cancel each other out. That makes the neutral charge on the compound. Okay, so remember that, swap and drop, and it works for every single time, every single time. Okay. All right, and so if we were going to draw that out using electrons, oops, that's the swap and drop. So let's look at what happens here with electrons. So we have, and sometimes on tests it asks you to show this out. So we're going to have this one come over here. Calcium is in the second group, so it has 2 valence electrons. So that's what those 2 dots are. These are Lewis structures. And then phosphorus, since it's in group 15, has the 5 dots. So we have these 2 dots that are come over here. So now we have phosphorus that has 2 dots. But if we look at the bottom of phosphorus, there's still a dot there that is left unpaired. So we have to add another calcium, and that's this calcium here with 2 more dots. So this dot is going to come up here and go there. So now that phosphorus has 6 dots around it. But if we look at calcium, it still has an electron there. So we have to add another phosphorus with 5 dots. Okay, this is going to come over here and go right there. So now we have phosphorus now that is lacking 2 electrons. So we draw another calcium. Okay, and this dot will go here, and this dot will go here. Okay, so that gives you 8 around phosphorus, and now we have run out of electrons on the calcium side. Both of those phosphorus have 8 dots around them, so that's going to be 3 calciums plus 2 phosphorus. Okay, so the formula is going to be Ca3P2. Okay. Now, if we look at that same thing with swap and drop, we can see that works. So the calcium, we have a 2+ charge here. And then the phosphorus, we have a -3 charge for phosphorus. Okay, so if we take this 3 and pull it over here, and we take this 2 and we pull it over here, we can see that it's Ca3P2. We get the exact same formula. Either way we do it, it doesn't matter. Okay. All right, so now we're going to talk about polyatomic ions. And I want you to go ahead and write notes on this, but this is not what we're going to concentrate on first. So if you look in your reference materials, we see this list of polyatomic ions. So let's break apart that word polyatomic. Poly means many, atomic refers to atoms, so it's an ion that contains many atoms. And if we look at these examples, we have 2 carbons, 3 hydrogens, and 2 oxygens. That's poly, that's many atoms. This all bonds together, and it has a -1 charge. So that's a polyatomic ion. And this particular polyatomic ion has the name of acetate. Okay, and then there's NH4 here that has a +1 charge. That particular name of that one is ammonium. So NH4, and we treat these just exactly like elements. So this NH4 has a +1. This chlorine has a -1 charge. So those cancel out. +1 cancels with -1. So we don't have to do the swap and drop. We don't have to do anything except smash these together because they equal 0 already. So the formula is going to be NH4. So we go ahead and write this same formula, chlorine Cl. All right. So magnesium here, another example, magnesium is a +2, and then OH, the polyatomic ion OH is right here. It's got a -1 charge. It's called hydroxide. OH is a -1. All right, so in order to cancel this +2 out and make a neutral charge, we have to have 2 of these OHs. So this is where, sorry, the phone is ringing. So this is where we're going to have to put parentheses around this because it's a polyatomic ion to show that we need 2 of these polyatomic ions that are OH. So we use parentheses around that because if we didn't, it would look like MgOH2, 2 hydrogens, and that's not what we want. We want 2 of this entire thing. So you use parentheses around it. Okay, and the same thing happens with swap and drop. So aluminum is a +3. Okay, we're going to need 2 of those to bond with the carbonate CO3 here. That's a -2. We're going to need 3 of those to balance out the charge. So aluminum 2, and then we have to put parentheses around this because we want 3 of this whole thing. So you put parentheses around the CO3. We don't change this 3. That is, think about this as one solid unit. You can't break it up or change anything about it. We just pull it down and we put parentheses around it, and then we add our 3 for the subscript. Okay, now I'm going to go back because I'm going to talk about naming. So when you're using just 2 elements, then like these, then the name that we're going to use for this is we're going to take the first element. We're just going to write the name of that element down. Okay, so this is calcium. Then we're going to take this element, and this is phosphate. Oops. So this is phosphorus. Sorry, it's not phosphate, it's phosphorus. This is the element phosphorus. And we're going to change this ending. So we're going to drop this off and change the ending to "ide." So this is calcium phosphide. Okay, and if we look back at here, on this one, we're going to take, and this is going to be sodium, because we're not going to change the name of the first one. This is chlorine. Okay, we're going to take this ending off and change it to "ide." So this is sodium chloride. We do the same thing to this one. It's going to be magnesium chloride. Okay, and on this third example, we have aluminum. And this is oxygen. So we're going to take the ending off and change it to oxide. So that's pretty simple. Now on polyatomic ions, it's just a tad bit different, not very much at all. So what we do on polyatomic ions is we just use the names of everything. Okay, so if we look at this polyatomic ion NH4 here, that's ammonium. So the name of this is going to be ammonium. And then this, since it's at the end, it's an element, we change it to chloride. We change the ending to "ide." Okay, now this is the only one that you're going to change this ending, okay, on the polyatomic ions, because this is the only positive polyatomic ion that we're going to use. Every other time, the polyatomic ion is going to have a negative charge, so we're not going to change anything. So this is going to be magnesium. And the name of this polyatomic ion right here is hydroxide. So we're just going to pull that name over, not changing anything about it. So the name of that is magnesium hydroxide. On this one, this is aluminum. So we're just going to keep that name, not change anything about it. CO3 is right here. It's the carbonate ion. We're not going to change the name of the carbonate ion. We're just going to keep it. So this is aluminum carbonate. It's very simple. All right, and so that's what we're talking about here. So write these down. Never change the polyatomic ion name. Never change the first element name. And you change the second element name to have an "ide" ending. Okay, so write those down. All right, on transition metals, it's the very exact same things we've been talking about, but in transition metals, because the charges vary in these transition metals, sometimes we have a +2 for copper right here. Sometimes we have a +1 for copper. Copper changes, okay? So the way that we make the compound is exactly the same. So remember, chlorine has a -1. So these two would cancel out. So we just smash them together. So that's the proper formula for that one. But because the charge changes, here we have a +2. So on that copper, and then remember the chlorine's a -1. So we're going to have to swap and drop, or we're going to have two chlorines. So it's going to be CuCl2. So we need some kind of way to distinguish whether this copper was the +1 copper or the copper was a +2 copper, so that we can get the formula right. So all we have to do in naming of these is just tell what the charge of the copper was. We use a Roman numeral in the name to do that. So this is going to be copper 1 chloride, okay, because we used copper 1. And the name for this one is going to be copper Roman numeral 2 chloride, okay, on that one. So that's very, very simple. So that's the only difference when you're using a transition metal, is you have to use a Roman numeral to indicate what the charge of that metal was, what the ion was. Okay, so here's some more that we have to name here. And if we use a polyatomic ion as opposed to a main group element, it's the very exact same way. So on this is copper 1. And then SO4 is a polyatomic ion called sulfate. So it's the very exact same rule. We just keep the polyatomic ion name. Okay, here sulfate's a -2. Copper here has to be a +2 because we don't have a subscript there. So this one would be copper 2 sulfate. Okay, so there's no difference in naming except for we use the Roman numeral. Okay. All right, and so we're going to have more practice here writing some formulas from names. So here we have iron that's got a +2 charge, and we know that because of the Roman numeral is a +2. And then carbonate, which is a CO3. We look back at our polyatomic ion list, we see that CO3 here is a -2 charge. Okay, so these have the same charge, so it's just going to be FeCO3. Okay, and then iron 3 hydroxide. So this is iron +3. Hydroxide is OH, and that's a negative charge there. So we swap and drop. We're going to have Fe. We don't write the 1. And then OH is going to have 3 of those. So we had to put it in parentheses. 3, just like that. Okay. All right, and so we're going to do these one step at a time, and we're also going to talk about acids separately, so I'm not going to go over that here. So thanks for watching on this, and now I have a little challenge for you. If you watch this video all the way through, what I want you to do is I want you to click the like, subscribe, and the bell notification, and then leave a comment down below. And if you do this by 8 o'clock tomorrow morning, you're going to get a power-up. And I'm also going to put your name in a drawing for 5 power-ups. But you had to watch the video tonight when you're supposed to and do all of this by 8 a.m. tomorrow. All right, so again, slap that like button right across the face, click the notification, and leave me a comment down below. And we'll see you next time.